Chris here is paying attention. We can talk pre-launch, we can talk laboratory, we can also talk post-launch.
Can I pick you up on you showed us the modus drift in the sensor calibration, 20-25%. Is it 20-25% in the various modus? Was it modus sensors or?
Oh, the one at the bottom, that was AVHR.
No, you had 5 or 6 sensors.
Yeah.
And you showed them drifting in time.
Yes. That was AVHR.
Was it all?
Yeah, NOAA 9,
No, all right,
NOAA
yeah,
7,
yeah,
I'm
no,
sorry, yeah. That was the original
Yes.
solar orbiter systems, yeah. Modus was much better than that.
Now, maybe I'm jumping ahead, but with the carriage calibration, you can do the correct for that.
So if you saw the talk I gave in this meeting, I put an updated chart from Eric Vermote, which showed the 4 of the AVHR systems where he's removed the difference. So it's that chart, except now everything's flat. Yeah. So now I'm going to talk about the reflectance-based method. And the reason is, again, so all this background was to convince you that, well, it's background of calibration, and it's kind of terminology, methodologies, approaches. Now I'm going to go into a discussion of an overview of the reflectance-based method. And the reason is, one is the person in the upper left. That's a younger version of myself. It hasn't been that long since I've been doing this, but that picture was quite a bit ago. And the reflectance-based method is one that was developed in the 1980s by the group at the University of Arizona, and Phil Slater was the guy who hired me after I got my PhD. So I was the guy who was hired to handle this radiative transfer code part. And then I found out I didn't mind actually carrying spectrometers across the test site. I also have done quite a bit of work in characterizing the atmosphere using solar radiometers. So for me, this was a nice extension of my radiative transfer modeling and putting it to use in real life. And the goal was to try and characterize what's happening at the sensor in terms of calibration. So the basics of the reflectance-based approach is you measure the ground, you measure the atmosphere, you put it into a black box, and that black box predicts the radiance at the top of the atmosphere. It gets compared to the sensor output, and that comparison tells you whether or not it's calibrated. And just because I had another version of it, what we basically do is we take the surface measurements and convert them to a reflectance. We take the atmospheric measurements and we convert them into information primarily about the aerosol size and the aerosol amounts. Those are the 2 key things that we have to get out of our measurements. And then those go into the radiative transfer code, which mixes it all up and basically can tell you where all the photons are going. And then that gets you that prediction of top of atmosphere. I like it because when I teach remote sensing, it's the whole problem. And it's more in the forward direction than it is the backward direction. Most remote sensors, they start with the imagery and they want to get to the bottom. Well, if you're a radiative transfer person, it doesn't matter whether you go up or down, it's still fun no matter what. And in this case, we're making measurements out of wonderful, glorious sites. The thermal guys, they go to Lake Tahoe in Nevada. Lake Tahoe is a resort. It's a very nice, beautiful lake. It's up near the ski slopes. And this is Railroad Valley. There are no ski slopes. And it's Railroad Valley dry lake. So even our lakes are not with water. So when you're in the reflected solar, you're not very smart. Pretty places. But the work is still refreshing and it's still rewarding. Over the years, the methodology has been shown because it's very simple, very straightforward, and it's been extremely successful. It's been applied, when I left Arizona, we had applied it to more than 50 imagers over time. And there's a reason everybody kept asking us to do it is we got to where we were doing it the same way, and so at least they could feel comfortable at about a 5% level whether their instrument was operating properly. What's nice is it's not difficult for a group to get into the business. Even if you have, we could go outside and in Beijing with a modest amount of effort, if we found a big enough, in fact, I'm not sure which side of the building, over there, the Olympic Park area, there's some large expanses of both asphalt and concrete and grass that we have the right equipment and did a little effort, we could get to answers that are better than 10%, absolutely. Even with this murky atmosphere. If we knew that it was clear, that it was just pollution, not clouds that were up there, we could get to an answer that's reasonably good. It's a straightforward methodology. You just have to combine all the pieces properly. The experience and the protocols are what allow you to get to improved precision, and then the biases is what we're still trying to figure out. And my hope in this kind of training course is the more people that see this technique, the more people that see this methodology, whether you use it for validation of surface reflectance, or you're using it for validation of PRI or NDVI or anything else, the techniques are there. We'll start to find biases between different groups doing similar techniques, and we'll figure out what's causing those biases. Because I'm right now, by the end of this, you'll hear me basically say, I'm stumped. We're at a point where everything's at about the 0.5% to 1% level, and we cannot figure out easily how to just jump it down and get rid of those 0.5% or 1%. So the advantage, reflectance. So at the very beginning, it was we're going to measure the surface. And the surface, we could measure radiance, but we're actually going to use reflectance. The reason we chose reflectance is the instruments are not that good. They vary with time, they have temperature effects. For those of you that know about the ASD, you also know that between 900 and 1,000 nanometers is a big jump because the silicon detectors are warming up and so forth, and there's all sorts of problems there. By going to reflectance, we can remove those effects, in theory. Now, there's still some things that have to be done to get rid of that, but the absolute radiance, it gains us a bit in terms of the uncertainties. It allows us to use more portable instruments. We can put this in place, in fact, from an aircraft, as long as your system were stable over the time of when you calibrated on the ground and when you flew it. So the Avris team, now they do basically a reflectance calibration prior to flying the aircraft. They bring a system underneath, and it's a lamp-based system, but it's a lamp with a panel. And as Chris was showing, that basically what they do is they just assume their lamp has been stable, and they know the reflectance of the panel, and they go into a reflectance mode on the cal of the system. The other nice thing about doing reflectance is, remember that cosine solar zenith angle problem, cosine law? If sun angle is changing with time, and we know it does because it gets dark at night, if you're making measurements and I try and calibrate a system, let's say at 10 a.m., and I want to calibrate another system at noon, and maybe something happens that I cannot make the measurements at noon, if I'm in reflectance, I can assume the reflectance is stable with time. Not a perfect assumption, but it's a much better assumption than assuming that the radiance is stable in time. And so by going to reflectance, we basically now have something that doesn't change as much with time. So in terms of surface reflectance, it's a pretty straightforward process. You strap into an ASD, and for those of you that have the newer ASDs that go on your back and others, this gives you an idea of how old this is. It's still in operation. This was the 86th version of that ASD built. The group that I worked with at Arizona had the 13th one and the 86th one. And I pretty much use this one every time I collect it. And even worse, anybody ever heard of Windows 3? That's what the computer's running, Windows 3. The idea is that you have your ASD, you set it up appropriately, we put a four optic for an 8-degree field of view. You have a white panel, Spectralon in this case. Spectralon's reflectance calibrated, it's level. Take a measurement of that. And then you go out for a hike. And you sample the surface. And by taking the ratio of the measurement over here to the measurement here, you go to reflectance. And you can go to spectral reflectance. And so you can see the shape of a typical clay ply surface. This isn't 0, this is 0.25 down here, up to 0.45. It's a fairly flat reflectance, and hopefully nobody knows what this is. Somebody told me it's illites and clays and kaolinites and other things, and they can look at that and they can tell you exactly what's in it. To me, it's dirt, and it's fairly uniform and fairly randomly distributed. But it looks brown because we don't have much reflectance in the part of the spectrum. Atmosphere. So the dominant way that most groups do atmospheric measurements is you have an instrument that has multiple wavelengths. Every little black dot there is a different spectral band. There's a little detector up on the top there that helps point at the sun, and it just tracks the sun all day long. It does it automatically. Here's version, this was a newer version. So there's a new version, there's the original version. It's just better mounts and better tracking and better setup and things like that. You can see the students there on the right-hand picture, gives you an idea of scale. But by taking the measurements of the sun, looking through the atmosphere, if you have the instrument calibrated, you can get transmittance through the atmosphere. That's a function of wavelength. And then that information allows you to retrieve all sorts of other information like ozone, water vapor, aerosol amounts. This was really fun for me because my master's work was in retrieving water vapor amounts using this technique. So then I got to get a job where basically I was being paid to even keep doing that. So in the retrieval, as a function of wavelength, we can get the optical thickness, which is related to the amount of stuff in the atmosphere. We can do that as a function of time. So what happens is at a single wavelength, this is 440 nanometers, that allows us to measure at 440 nanometers what the optical thickness is. That's related to the total amount of stuff in the atmosphere, both dust and molecules. From that, we can also then derive what's happening as a function of time at some arbitrary wavelength that would match our sensor. We can also then retrieve information about the sizes of the particles that are in the atmosphere. And we can get information about the amount of column absorbers of water vapor as a function of time. So from just 10 measurements, 10 different wavelengths, we can derive a whole slew of other information about the atmosphere. And then that goes into our rating to transfer code to do our calculations.
Can I butt in again?
Yeah. No.
Is that assuming that you know what the top of the atmosphere sunlight is?
No.
No.
And I'll get into the details. We use what's called the Langley method. The Langley method, if you have an absolute Kelvin, you can get the solar air radiance. We just assume that it's not changing for a given band, and then we just get the transmittance. Rating to transfer code, there are numerous codes. I'll anticipate the question. Kurt, what rating to transfer code should I use? Answer. I have a better answer. Find out the rating to transfer code that the person in the office next to you is using. That's the code you want to use. Because when your code run breaks, and you cannot figure out why you're getting a really bad answer, you will go across the hall, next door, next desk, and ask, okay, I'm trying to do this rating to transfer code run, and I'm not getting a good answer. What did I do wrong? The codes themselves agree really well with each other. And so it really is, if you're starting out brand new, so if you already know that you're using Modtran, everyone who heard somebody say Modtran or say 6S or something, make sure you know who that person was, so when you start out, use whatever code they're using, because they already know, and they already know how to run them, and they already know what mistakes are. And like Modtran, I learned to run Modtran back when TAPE5 files were the only way to use it, not with the GUI interfaces and things. We would text edit the TAPE5 files. It's not my favorite code, but now I'm starting to use it more and more because there's all these wonderful ways to write interfaces to it. 6S, I use it now more than I used to because Eric Vermote is now at NASA Goddard, and Eric Vermote wrote 6S. So I have the code developer just across campus. He's one building away from me. And he was at IGARS, by the way, if you had a chance to see him talk. Gauss-Seidel iteration is my favorite because that's what I did my dissertation on. And so almost everybody at the University of Arizona ended up using Gauss-Seidel because it was written by Dr. Benjamin Herman, who was a faculty member there, and people started asking if they would go to him for advice on how to run the code. So it really is, there's no best code. It really comes down to is whatever resources you have for getting answers to questions. That's the important thing for me. So the differences are the basic algorithms. We'll talk some more about the rating to transfer code. What's nice is, for reflected space methodology, we're going to be using bright surfaces typically. Reflectance is at least more than 0.1. If you're using less than 0.1, you're in the ocean community, and that's something different. And for the near native views we're going to use, and we're going to pick sites that are fairly clear atmospheres, the radiative transfer code really makes no difference. It's going to be what we put for the inputs and how we parameterize those inputs. So the other part is now you have to get that, so after the radiative transfer code, we have the top of atmosphere radiance. We now have to compare that to the imagery. And if I took away those dots and said, find the test site, 30 years ago, that was not easy. Now, again, it's gotten much simpler. The geometric information, the geographic information with the imagery is much better now. That most people I know, they rarely will put out these markers because they can just use the geometric, the geographic information, and the imagery to find their test site. But in the old days, it was still a nice way. We laid out, we would put a rectangle. That was the area that we walked. And so you put a blue tarp at the two corners, and that allowed you then to put the rectangle in the imagery, and that allowed you then to figure out what the average digital counts was for the instrument, which then allowed you to get to a calibration coefficient. We compared that to the top atmosphere radiance. Notice that this site is not perfectly uniform. The advantage of the reflectance-based approach is we do not need a perfectly uniform site. We need a site that we can sample it appropriately to characterize the non-uniformities. And so what you'll see as we start talking about is people are walking around in various locations along this area to sample that spatial heterogeneity. If it rained, that again is not a problem because we're going to be on the site, if possible, if it's not flooded. So again, we'll try and make measurements, and by being there at the time of overpass, we can characterize everything. That's the other nice thing about using that for this course, is it simplifies a lot of these difficulties, a lot of these confusions. The type of imagery that you use, though, has always been a debate. When I first started this, it was level 0 data only. You never touched anything that was resampled. You never touched anything that had been processed. You want the raw data, and you had to deal with basically doing your own geometric correction where this location is the same in both. These are MODIS data, level 0 MODIS data, and because it's a scanner, when you get the level 0, all they do is they just throw all the data out there, and then you have to figure out how to correct for the scan-to-scan differences. Because it scans one direction, and then it scans back the other direction, basically, in terms of its paddle wheel. And so everything gets off by a little bit because of the two different sides of the mirror. Most of the sites that we're working with are fairly uniform or characterizable. Most of the data that we're dealing with now is being used by the applications community. And I'm a firm believer in, I want to see what the users have been working with rather than trying to do perfect sensor characterization. So if I can get to where I have a level 1 data product that's been calibrated and geometrically and geographically corrected, and I have a 10% error in that, then I know the users are going to have a 10% error at least. And then I can go back to the level 0 and figure out what the cause of that is. So I will always try and go as simple as I can. In this class, you're not going to see this type of imagery again. I think I use it one more time when I go through a specific example. But I would rather go to the level 1 data that the users would have access to, that at least there's level 2, level 3 type data products. And that's a different philosophy that I have relative to a lot of my colleagues that are true, real sensor characterization, calibration people. I come somewhat from the other side where it's on an atmospheric type and I want to see where the data is going, not just view it as an instrument calibration. Right? So that's the overview in terms of the methodology. I'm going to go through an overview now by showing some of the results and how we use these data sets. And it's just basically was a random collection of charts that I had from a bunch of different talks. But the one I always like to start with is Landsat 5 thematic mapper. So again, it was launched, and this is time since launch, 25 years. They finally turned it off 2 years ago, I think. It was just an incredible platform, worked wonderfully. These are band 1 data, should be. Gain, calibration information. So if the instrument had not degraded at all, then all these data would be on a flat line. The blue line are the lamp data, internal calibrator. IC is internal calibrator. The desert site data, these were done using the Libyan desert. And they went back in time once they realized the lamp data were not quite what they thought it should have been. The red dot was a cross-calibration between Landsat 7 and Landsat 5. So Landsat 5 is up in orbit, it's going around and around and around. When they launched Landsat 7, they launched it so that it basically came underneath Landsat 5. They had 3 days where they all went together, and then they put Landsat 5 out, or Landsat 7 out 8 days apart from Landsat 5. So then there was no way that they could do it. But this cross-cal point was an anchor that said, we know what Landsat 7 is, so we know what the answer is here, and that value is set. So this is the marker that everything basically was forced to. They forced the internal calibrator at that point, they forced desert data. These purple triangles, those are the reflectance-based results. And I take great pride in this. So, 1980s, Phil Slater's running a group at the University of Arizona. 1, 2, 3, 4. 4 data points over 5 years. And then funding stopped. And if you're a university professor, funding stops, data collection stops. And then you hire some guy who's not a very bright postdoc, and you give him projects to do. So these were my first 2 calibrations for Landsat 5. Now, what I like to point out is the early ones, like the group in Arizona, didn't quite match up very well with the internal calibrator or the desert stuff. And my data did pretty good, so I felt pretty good about myself. But then look at the number of data points. And this is partially, again, with funding. And we were launching the EOS missions, the Terra mission, the Aqua mission, Landsat 7 was being launched. And the philosophy used to be, do a few trips perfectly. And mine was, do a bunch and see what happens. Do a lot and see if you can figure out what's going on. And so we got much better in terms of the sampling that we had. But you can see that at least there's information, and we still have no great confidence that these are truly different. There could be some biases. But the accepted calibration was basically set on the desert model. And that became the new revised Landsat 5 calibration. There's one last bit. I spent way too much time on this already, but there's one last bit here. It took us 25 years to change the calibration of Landsat 5. 5 years in, we have at least a 15–20% change in the calibration. And nobody had the courage to say, we should change that. Let's get another data point. Let's get another data point. Let's get another data point. We wasted a lot of time. And it's because we did not trust our error budgets. We did not trust our uncertainty traceabilities. We did not trust the fact that, yes, there is some variability here, but we know what the answers are. We know there's been a change. We need to change things. And that's one of the things I hope you get out of this training course is that if we get good at doing our error budgets, the people who say, no, we're not going to change that until you can prove it, we can come back and go, we have proven it. You do not understand math and science. You need to change your calibrations. ETM plus temporal results. So this just goes and shows the number of data points that we've collected. The pre-launch calibration is the green line. The blue line is the average of all those red squares. So we're pretty confident that the calibration did not change. And these are an actual counts per radiance. This is a calibration, not a, I'll show some results of the radiance validation. So we took the counts from the level 1, level 0 data from Landsat, and divided it by our predicted radiance to get a counts per radiance, and then compared that to what they claimed the calibration should be for the system. What you take away from this is there's a lot of scatter. There's some very odd data points that look like they should not be there. So we're trying to understand what causes that, and that's where the uncertainty and the error budget analysis comes into play. But by having this number of data points, at least you start to get a confidence in terms of understanding, what is the variability, what is the repeatability of the methodology, what are the relative uncertainties and the absolute uncertainties. The other bands show similar results, and some other key little interesting things I'll show, but you'll see a lot of Landsat 7. Even though this is imaging spectroscopy, I just have so many data points. For Hyperion, I only have 7 total through my whole career. For Avarice, I think I have 3 total throughout my whole career. But when you start talking Landsat, you start talking Aster, you start talking about 50, 60, 80 data points. And so you have a lot more data, and that's why you'll see multispectral examples. The reflectance-based method doesn't care if it's multispectral or hyperspectral. So doing it as a function of all the bands, and again, taking the average and the standard deviation, and this is now a percent difference from the reported calibration. And Andreas was back to playing golf. And you see basically, somewhere around 4 or 5% differences between the calibration of the system and what the Vicarious calibration reported. And that's within the uncertainties of the combined uncertainties of both methods. So by this, you say statistically we cannot say there was a change in the Landsat 7 calibration going to orbit. The error bars here are the absolute uncertainties that are estimated from the error budget that you'll see later on. And in most cases, what the disappointing part of the reflectance-based methodology is the relative uncertainty, which I'm using as the standard deviation here, which is not quite right, is very similar to the absolute. And that's the big problem with the Vicarious methods and reflectance-based in particular, is until we can get to where this relative uncertainty is a factor of 10 less than the absolute, we're never going to be close to what the metrology people know how to do it with data sets and statistics. And then you can show it in terms of radiance versus radiance. So image radiance versus predicted radiance. And what that shows is, you get up here, there's a little bit of a tilt. And the question becomes is whether that's statistically significant. It wasn't when we did the analysis to begin with. And it's just trying to understand, because the other problem is it becomes band dependent also. And all the bands tend to cluster in terms of, band 2 typically has a higher radiance than, say, the SWIR bands 5 and 7. And so you have to then take into account, well, maybe I had a band that was biased, and then that shows up as a problem in terms of how the reflectance-based methodology shows results. And it's when you start looking at the ensemble of everything, and you try to tease out, I see a difference, try to understand the difference, and then it feeds back into whether I need to handle a different uncertainty budget. We can use this for cross-calibration also. So if you start and take the view that the reflectance-based method characterizes the surface, much like you do a spherical integrated source in the laboratory or a panel in the laboratory, then you can compare them. And what's nice is you're collecting all the data spectrum. And all the top of absolute radiances are hyperspectral, so you can band integrate to match any sensor you want. And it can be tailored for the specific overpass of that sensor. So it's the perfect simultaneous nadir overpass, except you don't need it to be simultaneous, you don't need it to be nadir. You can just compare as you go. And what's nice is we showed that for a lot of the systems, Aster, Modus, ETM Plus, and Miser, these are all the morning ones, they're all the same day. And ETM Plus is about 30 minutes different than Aster, Modus, and Miser. And Aster, Modus, and Miser are on the same platform. So they're seeing everything at the same time. And what you notice is that they pretty much all agree within 5%. And it does not matter to look and see how it compares to 0, which would be a perfect agreement with reflectance. What you're doing is comparing each of them to each other. So in this case, the triangle, Modus, in this particular band, is a bit different than the other bands. And is that significant difference? And that's where the error budget comes in, is what's a real difference. These results were done before the most recent Aster calibration. So Aster band 1 shows up as a little different than the others. We now know that it was significantly different than the others and needed to be recalibrated. And more of those, and make sure I at least got in something that showed hyperspectral. So there's Hyperion data showing up, and you can pick out the bands that match most closely. I can put far more Hyperion bands on here if I wanted to. I did not have to convolve the Hyperion bands to match the other bands. What I do is I convolve the reflectance-based results to match the Hyperion band. So this is a true calibration of the Hyperion system, and it's an average of the 7 dates that we had for it. So you can see that it has some large uncertainty because of how the signal noise at short wavelengths. That improves as you go to the longer wavelengths. What was always nice and interesting to note was out here at 860 nanometers, get out to the near infrared, everything tightens up. Standard deviations get smaller. Differences get smaller. When I saw that, it was just like a magical thing, and Chris has already figured it out. No? Oh, I thought that's it. The highest signal-to-noise ratio of every system operating with silicon is around 860 nanometers. You have the peak, you have the output of the sun hasn't dropped that much, so you have high output of the sun, you have high responsivity of the detector package. At longer wavelengths, you have higher responsivity of the detectors, but lower solar output. At 860 nanometers, your ground instruments work better, your flight instruments work better. Your lamp system in the laboratory works really good because you have good output. Everything works better at 860 nanometers. And so this is, I always point, because at some point somebody's going to believe me that I know what I'm talking about and they're going to understand it. The reflectance-based method works when the ground instruments are in good shape and the on-orbit systems are in good shape. All of these others, I keep trying to explain, I tell people is I can't tell you for certain if it's mine or yours. I'm pretty sure, especially when I start getting good results in 3 instruments that were calibrated differently by different groups, and I have some other outliers that maybe it's not reflectance-based results. But again, it has to be the error budgets. They have to be able to read the error budgets and understand them. And then just to show that I can do Hyperion at more than just a few bands. These are all the bands. And if you saw my talk on Tuesday at IGARS, you heard me pontificate that my complaint with the Hyperion group is they are unwilling to accept that those are real band-to-band differences. And when you look at the relative uncertainty from the reflectance-based result, you look at the standard deviations, these features are repeatable. They show up all the time. And so that's again where we have to get enough confidence that you think about the impact these little wiggles are having on your spectral signatures. They could be gone, they could be removed. But you have to have the confidence in the data set. That confidence comes from the error budget. In terms of the sampling, it becomes an issue for the case of Aster. We had several data points early on. This is band 1. The problem with band 1 is the data in level 1. 1B is typically saturated over a lot of the test sites that I use. If you go back to the other data sets, you might have some, but it still can saturate. So we did not get as many data points as we wanted during certain times. But it looks as though there's a trend. And then the question is well, we have these outliers. That makes it hard for anybody to believe that your curve fit is appropriate. We put an exponential in there because that's usually what the systems do when they're on orbit, is they degrade exponentially. But how you convince somebody that your answer is correct, again, goes back to the error budget. And just to prove it, both of those curve fits, the green line's a little hard to see, but that's the exponential. The red line's a linear fit. Statistically, they're both the same. If I do a statistical thing and say, does this curve differ significantly from a statistical standpoint from the data set? The answer is no. The same answer comes out from the green line. So there's a range of answers that still fit the data. We're trying to understand now, physically, we believe the top one because of the way optics typically degrade on orbit. The bottom one, we would not expect to see a linear degradation because it also gives us the answer that at some point, the system is unresponsive. If we go out to infinity, we go to a 0 response. And exponential is because they asymptotically go to some other value. Results versus time. This one still bothers me, and we've never been able to figure out, well, we're pretty sure what it is, but the instrument's gone now, so we cannot figure it out for certain. We were collecting data from Landsat 7. And all of a sudden, around day 1500 after launch, it jumped. And as near as we can figure, these data are the correct data over here. what happened back here is a really subtle nonlinearity in the ASD spectrometer that peaks in the green part of the spectrum. You can saturate certain detectors in the ASD, but it will not re-optimize until you get enough of the detectors to saturate, and then it will re-optimize. And we were collecting enough data points in the summertime and such that basically was skewing our data because these were becoming saturated and we did not know it. And then when we switched to ASDs, then all of a sudden the problem went away. And the hard part was we had to convince everybody that, well, no, these data are the right data. It's these that we think are problematic. And in here, there were multiple ASDs being used. And so because you have multiple ASDs, you then have multiple scatter points. But once that one ASD went away, then, and we also developed better techniques for optimizing, the problem seemed to go away. It was too late. We could not go back and prove it. We could only kind of use the new instruments and figure out, yeah, I think that's what's going on, and looking at the processing system. And it goes away in some bands. So again, it had to be something, we knew it had to be a nonlinearity because we were basically looking at a panel and looking at the ground and then coming back to the panel. It's a ratio methodology. So it had to be something that when you looked at the panel was causing the instrument to behave differently than when you were looking at the ground. And it was also because we knew our error budget should not have that difference between, in this case, this is band, I forget which one, this should be the short, this should be band 3, 660 nanometer, yeah, so band 3 of Landsat, and then you go out to the longer wavelength, the short wave, band 5, and it goes away. And we have nothing that should cause that, so it had to be some spectrometer that was making the measurement, and it was in the peak of the output, and then we then realized again it was an optimization issue.